Okay, welcome back. Today we want to do 5-8, which will give us kind of a mechanical method for finding these explicit formulas for recurrence relations. Unfortunately, it's only a certain class of recurrence relations we'll be working with today. The second order linear homogeneous recurrence relations. And if you took differential equations, this is exactly the same as what you did there with the second order differential linear homogeneous equations. There's the characteristic equation, and your solutions are based off of the types of the roots to that equation. And then you'll build your equation based off of certain forms. Okay. All right. So if you've done differential equations, this is easy, but if not, this may be a little more difficult, but it's highly mechanical. There's no guesswork like the iteration method. Okay, so without further ado, let me get this started and set it up. Hold on one second. Okay, so it's 5.8. They give you a lot of theorems in there. I think I'm going to approach it more in, this is how we do it kind of way, rather than going through proofs and stuff. So anyways, we have second order linear homogeneous recurrence relations. Okie dokie, so there it is. First, we want to start by just looking at the form. What do these things look like? So the Fibonacci sequence is the example you should have in your mind. So each term is based off of the previous two terms. Okay, hence the name second order, because there's two previous terms in the form. Things that look like second order linear homogeneous recurrence relations may not be, actually. For example, a sub k equals k times a sub k minus 1 plus 3 times a sub k minus 2. This is not in the form, and it's because of that pesky formula in front here. So the things in front of your a sub k minus 1 and k minus 2 have to be just constants. You can't have functions of k in front of them. Okay, so that's one example. Another example, you can't have anything where you're kind of like squaring these a sub k things. Okay, so you can't have something like this cubed plus 3a sub k minus 2. That's bad news there as well. Okay. And there's probably some more examples in the book, and some of the questions in WebAssign will kind of go through it, but it needs to be in this form for us to work with it. Otherwise, you have to try something else. Try iteration or something like that. Okay, so to find this form, like I said, we're not going to do iteration. We're going to use something called the characteristic equation. Okay, and that's just going to be a quadratic equation based off of the recurrence relation. So I think the best way to go through this is to go through a problem. Okay, the best way to show you how this works. So this is number 9. They give you the recurrence relation. B sub k is 7b sub k minus 1 minus 10 times b sub k minus 2 for k greater than or equal to 2. And then you're going to need some initial values to get the particular solution, so b sub 0 is 2, b sub 1 is 2, and the characteristic equation is based off the recurrence relation. Okay, so what I'm going to do is, instead of writing b sub k, I'm going to write t squared. Instead of b sub k minus 1, I'm going to write t, and then instead of b sub k minus 2, I'm just going to put a 1 there. Okay, so that formula, this characteristic equation right here, is basically just me substituting in t's for the b sub k's. Okay, it comes directly from the recurrence relation. Okay. Then I'm going to solve this thing. So I have to set it equal to 0, t squared minus 7t plus 10 is equal to 0, and then factor it. T minus 5, t plus 5, or sorry, t minus 5, t minus 2, okay, equals 0. And then our solutions are t equals 5 and then t equals 2. So the formula, the explicit formulas for the recurrence relation are built from these roots. Okay, so our general formula for the explicit formula is going to be something like, call it b sub n equals c times the roots, right? So we want 5 to the n plus d times 2 to the n. Okay, so the 2 just plop in there, the 5 just plop in there, and that's it. Okay, in order to get the particular explicit formula, we need to use the initial conditions. Okay, so the explicit formula, we're going to need the the b sub 0 is 2, the b sub 0 is 2, and then b sub 1 is also 2. Okay, so from there you're going to build a system of equations. So you'll get something like what? I don't know. So how does this work? So if I have b sub 0 equals 2, what you're doing is plugging the 0 in to the recurrence relation. Okay, so I'm taking this number here and plopping it in for n into this equation. Okay, so what do I get then? I get b sub 0 equals c times 5 to the 0 plus d times 2 to the 0. And then b sub 0 is 2, so I can replace b sub 0 with 2. 5 to the 0 is 1. 2 to the 0 is 1, so I just have 2 equals c plus d. Okay. Then I have b sub 1 equals 2, so I use this condition to rewrite the formula. So when I plug in 1 for n, I'll have b sub 1. I'll have b sub 1 equals, where is it, c times 5 to the 1 plus d times 2 to the 1. Okay, and then of course b sub 1 is 2, so I have 2 equals 5c plus 2d. Okay. So you have a system of equations and you just solve that. So I'll start with the 2 equals c plus d and solve for like c. So c equals 2 minus d. Okay. And then I do a substitution method. So 2 equals 5 times c, which is now 2 minus d plus 2d. And then you could solve this for d. So I have 10 minus 5d plus 2d. Okay. And then 2 equals 10 minus 3d. And then subtract, I guess, the 10 over, and you get negative 8 equals negative 3d, and then d will equal 8/3. Okay, and then take that and plop it back into this first equation for c. c equals 2 minus 8/3. In other words, c equals 6/3 minus 8/3. In other words, c equals negative 2/3. Okay, and then we just substitute c and d back into the general formula for our explicit formula for the recursive relation. So b sub n will equal negative 2/3 times 5 to the n, and then plus 8/3 times, I think it was 2 to the n, right? Okay, and that's it. So it's just a highly mechanical way of avoiding having to do the iteration method plus induction. Okay, and it's a little quicker. The book will give you all of the technical details and all the proofiness for why everything works and why we don't basically have to do induction or anything. Yeah, but I mean, that's the mechanics of it. Let's take a look at some of the ones in the homework. One thing to note is the the general formula in general is based off of the types of solutions to that characteristic equation. So if you have, for instance, for us, we have two solutions, and those solutions can be real or imaginary. Two solutions. The general solution will be just as I showed. So it's b sub n equals c times, call it one solution s to the n plus d times the other solution, let's call it r to the n. Okay. If you have just one repeated solution, for instance, if it was t minus 5 times t minus 5, your form changes a little bit. So this one's, it's given in the book. I don't think it comes up in the homework, but just to note it, it would be something like this. And if you took differential equations, it follows the forms that you saw in differential equations, except you don't have to use Euler's formula or anything for the imaginary solutions. Okay. Okay, so there's that. Be aware you can have like r be 1, and in that case it will just be c times s to the n plus d, you know, things like that. And, okay, so anyways, let's try some maybe homework problems from the book and see how that goes. Or sorry, WebAssign, I guess. I want to look at WebAssign. If I could find WebAssign, we will look at, okay, I found it. Okay, and I need to kind of set it up so I can actually see it and do notes at the same time. Let's get rid of this thing. Crap. Accidentally. Okay, so the one in the book, they give us our recurrence relation, and I think this is number 5. Let me get rid of the blue pen. Okay, so number 5, let me sort of minimize some other stuff that was going on there. They give you a recurrence relation, b sub k equals 9, b sub k minus 1 minus 18, b sub k minus 2, and then they give you b sub 0 is 2 and b sub 1 is 5. Okay, so find the recursive, find the explicit formula. Okay, so our characteristic equation, t squared equals 9t minus 18. And again, I just got that from the recurrence formula. And then solve that. T squared minus 9t plus 18 is 0. And then t minus 9, oh, that's not going to work, right? 6 and 3 maybe will work. So 6 and then t minus 3. And so our two zeros are t is 6 and then t is 3. And so our general solution, it will be c times 6 to the n plus d times 3 to the n. And then we need to find those the c and d, and we use 2 and 5. So b sub 0 is 2, b sub 1 is 5. Plug that in. So I'll have 2 equals c times 6 to the 0, which is 1, plus d times 3 to the 0 is 1. And then from the other initial condition, I have 5 equals c times 6 to the 1 plus d times 3 to the 1. Now we have a system of equations. Let me rewrite this guy. And I'll solve the first equation for c. c equals 2 minus d. And then substitute that expression in for c over here. So 5 equals 6 times 2 minus d plus 3d. Okay. And then 5 is 12 minus 6d plus 3d. And then 5 is 12 minus 3d. And then 3d will equal 7, apparently. And then d equals 7/3, unless I made some arithmetic error, which I do a lot. But 2 minus 7/3, back substitute now, back up here. And so c equals 6/3 minus 7/3, which of course is negative 1/3. And now we could back substitute into our general formula for the explicit solution. B sub n will be negative 1/3 times whatever. and then plus 7/3 times whatever. So what are our whatevers? 6 and 3. Okay, so 6 to the n, and then 3 to the n. Okay. Okay, let's do one more. So they can get kind of nasty when you have imaginary solutions. So let's try one of the imaginary solutions and see how that goes. If I can find one. Oh, here's one. Okay, so let me write out that problem. This is number 7, maybe. We have b sub k equals 2b sub k minus 1 minus 10 b sub k minus 2. When you do the Fibonacci, if you're going to do that one, let me get the initial conditions as well, you'll end up with square roots in your answer, and that's annoying too. Okay, the square root version is in the book. I'm not going to do it. I'll just do. I don't know if there was one in the. I don't think there's one like that in the homework, so I'm not going to do it. If you want to read about it, if you're all into the Fibonacci sequence or something. You can. Let me just focus on this, okay? All right, so again, I'm going to write my characteristic equation, which will just be t to the 2 equals 2t minus 10. And then you solve, set it equal to 0, minus 2t plus 10. 0, and you fiddle around with it, and you realize, okay, there's no way I'm going to get a nice factorization, so you have to go to, guess what, the quadratic formula. So negative 2 is 2 plus or minus the square root of b squared, which will be 4 minus 4 times a times c, all over 2 times a, which should just be 2. Okay, and then that will be equal to 2 plus or minus the square root of 4 minus 40 is negative 36 all over 2. So that would be 2 plus or minus 6i all over 2. So our solutions 1 plus or minus 3i. Okay. Okay, so now I want to form my general solution. What the heck did I say that was? B sub n equals c times 1 plus or minus 3i. Use either one. I'll go 1 plus 3i to the n, and then plus d times 1 minus 3i to the n. Okay. Okay. So now I use my initial conditions. They're both 9. So b sub 0 is 9. B sub 1 is 9. Plugging in b sub 0 is 9 into the general form. I get 9 equals c times anything to the 0 power is just 1. So it'll just be c times 1, which is c. And then plus d times this thing to the 0 power, the 1 minus 3i to the 0. Anything to the 0 power is 1. So that'll just be d times 1, which is d. And then plugging in 1, I get 9 equals c times 1 plus 3i. And then plus d times 1 minus 3i. Okay. And now you got some work to do, right? It's a system of equations that you're probably not used to dealing with because there's imaginary solutions. It's not a big deal. You just go c equals 9 minus d, and then you're plugging that in for d here, or sorry, for c. Right? So 9 equals 9 minus d times 1 plus 3i plus d times 1 minus 3i, and then that will be 9 equals 9 plus 27i minus d plus, minus 3di plus d minus 3di. Okay. And don't worry if things don't look like they're working out, they usually do. So I have 9 and then minus 3i. So 27i minus 30i is minus 3i. D's cancel, and then we have a minus 3di. I'm looking for what is I. Subtract 9 from both sides. 0 is negative 3i minus 3di. And then I can add 3i to both sides equals negative 3di. Divide both sides by, guess what? Negative 3i. And you end up with d equaling 1. All right, so nice I go back up here, c equals 9 minus 1, which equals 8. Okay, so those are our initial values, and now we just substitute them back in for our explicit formula. B sub n equals 8 times, I think it was 1 plus 3i first to the n, and then plus 1 times 1 minus 3i to the n. Okay, so it looks weird, but it is what it is, and that's about it. I'm just looking to see if I made any mistakes. Hold on. No, I think that's, whoops, did I make a mistake somewhere? I must have. Oh crap, are you kidding me? Let's go back and look. Did I get the plus 3i and the minus 3i good? Yeah, I got that's right. So it's just my C and D are wrong for some reason. Let's take a look. Oh, that's a D. That's not 30. It's, oh gosh, my writing is so bad. It's right here. I screwed up. Sorry about that. Fudge. Okay, so let me do some erasing. And, see how. Okay, please give me the eraser. Okay, so let me just go back here. Sorry, I apologize. If I employed an editor, I'd have them go back through the video, but I do not employ an editor. Okay, so again, FOIL. So I got 9 plus 27i minus d minus 3di plus d minus 3di. That'll be 9 equals, let me get rid of this junk too. Probably have to get rid of the junk below there. Okay. I'm getting compulsive about getting rid of the junk. Alright, so I'm just combining like terms. The d's will cancel. So I get 9 plus 27i minus 6di. Then subtracting the 9s, those will cancel. Subtract the negative 27 to the other side, equals negative 6di. And then divide by negative 6i. And then we have the answer. Okay, sorry about that. So that would be divide both top and bottom by 3i. You get 9 all over 2. And then we need to back substitute that expression up into here. So c minus equals 9 minus 9 by 2 is just 9 by 2. And then we could back substitute into our explicit general solution to get 9 halves times 1 plus 3i to the n plus 9 halves times 1 minus 3i to the n. Sorry about that. Okay, that's the spiel. Highly mechanical. The theoretical stuff in there is the most interesting stuff to me. I won't bore you though. You can read it on your own if you want to. Otherwise, you know, so there's big questions out there. How do we know that this only gives us this gives us all of the solutions, this form, you know? How do I know that? How do I know there's not some other weird solution out there that this does not characterize? Questions like that, you're going to have to delve a little deeper. You study again when you get the differential. Okay, I'll let you go though. All right, have a good night or day.